In this video, I'm going to demonstrate how to carry out an independent samples t-test using SPSS. The independent samples t-test makes the assumption that you have a categorical independent variable with only two levels and a dependent measure that is measured at an interval or ratio scale of measurement. And so the basic idea is that we are testing our sample means from the two groups to determine whether or not we should infer that there are differences in means at the population level. So in this particular data set, this is actually coming from a number of different public websites. Some of the variables in the data set are coming from the CDC, others are coming from the Bureau of Labor Statistics, others are coming from various education websites. So this is actually state level data representing all 50 states in the U.S. And what I thought I would do is compare the states on a couple of measures. So one of the things that I wanted to do was just to test whether there are differences between those states with and without the death penalty in terms of several outcome variables. Now, I want to make it really clear that we have essentially a population of states that are represented in this particular demonstration. So when you're carrying out the independent samples t-test to compare groups, the basic idea is that the groups are assumed to come from separate samples. So when you have population data, technically there's no real need to test for statistical significance because you have the population of observations that are already available to you. So you can just simply look at the means and tell whether or not there's a difference. But for this demonstration, I'm going to actually demonstrate the procedure. We're going to use significance testing, and we're going to treat the data as if it were coming from different samples. So what I'm going to do is begin by just going to analyze. I'm going to go to compare means and then go down to the independent samples t-test option here. So I'm going to click on it, and I've already been kind of working with this, but I'm going to demonstrate it anyway. So I'm going to go down. I've just reset everything, and so I'm going to put my independent variable or the grouping variable into the grouping box. So I'm going to scroll down a little bit. There's death penalty, and I'm going to put it into the grouping variable box. So in the data set, by the way, just to kind of show you what I'm talking about, there's the death penalty variable, and it's a nominally scaled variable. So it is a categorical variable, and let's say that I want to look at group differences in terms of violent crime rate. So, and this is from 2016 right here. So this particular variable is a scale variable, and what I'm going to do is I'm just going to click on it and move it over to the test variables option or box. So now I can, for the grouping variable though, I also have to assign values for the two groups. So with the death penalty variable, there are actually two values that are represented. There's a value of 1 represents a state with the death penalty, a value of 0 represents a state without the death penalty. And it looks like from the original data set that I was working from, there were a couple of missing values there. So in that respect, we are actually kind of working with some sample data. So at any rate, I'm going to click on Define Groups, and for Group 1, I'm going to type in 0, and then Group 2, I'm going to type in a 1. So the 0 and 1 designations as Group 1 and Group 2 are arbitrary designations, but they do represent the two different groups. So you have to keep in mind the coding when you are looking at your outcome results. So we're going to click on Continue, and so now you can see it highlights as death penalty and then 0, 1. Next, I'll click on OK, and there you go. So here are our t-test results. So you can see that basically we have death penalty. So again, the zeros is reflecting no death penalty, 1 reflecting death penalty. So you can see that we had 17 states that did not have the death penalty, and we had 31 states that did have the death penalty or do have the death penalty. And so obviously this is a subset of all 50 states. So in terms of the violent crime rate per 100,000 from 2016, the violent crime rate was basically the mean was 361.8, whereas for among the states without the death penalty, among those states with the death penalty, the mean violent crime rate was higher at 387 point, roughly 0.58. So in other words, it looks like the violent crime rate was actually higher in those states with the death penalty. Now, is that difference between these two groups statistically significant? So keep in mind that with the independent samples t-test, you're testing a basic, the null hypothesis is that there is no difference between population groups with respect to the dependent measure. So we can specify the null hypothesis in the following way. We can say mu 1 is equal to mu 2, which is basically the mu for group 1 is equal to mu for group 2. So in other words, and mu is essentially the notation for population mean. So essentially the mean for population group 1 on the dependent measure is equal to the mean for population group 2 on the measure. We could also lay this out as mu 1 minus mu 2 is equal to 0, meaning that there's no difference. So the basic idea is that we have our two groups. We have those states without the death penalty and with the death penalty, and we're going to be computing the sample mean. So the sample means that you see right here, these means, if you were writing this up for a publication, you would basically be designating these as X bar. So it would be, X1 and X bar 2 for group 2. And so we use the sample means and then test the difference in those sample means to determine whether we should reject this state of affairs in favor of an alternative hypothesis. So the alternative hypothesis, we can lay it out in the following way. We could say, for instance, we could say mu 1 is not equal to mu 2. Or if we wanted to state it a different way, we could say mu 1 minus mu 2 is not equal to 0. So just keep in mind that essentially, the mu's that you have right here, they're being estimated by the sample mean. So, keep that in mind. So the sample mean for group 1, sample mean for group 2 are being utilized as estimators of the population mean. And so what we're doing is we're trying to determine if the difference in the sample means is great enough that we can infer that any difference that's actually being observed between them and our sample is just really a reflection of sampling error as opposed to some real population mean difference. So at any rate, when we specify our research or basically alternative hypothesis in this form of mu 1 is not equal to mu 2, or if we've stated it as mu 1 minus mu 2 is not equal to 0, this is what is referred to as a non-directional hypothesis. And basically, what we're doing is we're testing to see if there is a difference between the groups. And we're not really making any kind of statement about whether the mean for one group is greater than the mean for the other group, only that there is a difference between the two groups. So with a non-directional hypothesis, and I'm just going to write in NDH for non-directional hypothesis. A non-directional hypothesis implies, when it comes to significance testing, it implies a two-tailed test. And I'll kind of talk briefly about that in a second. So that implies a two-tailed t-test. And so when it comes to there is another possible kind of alternative hypothesis that we can work from. And that hypothesis would state, is basically directional. So a directional hypothesis might state the following. We might say mu 1 is greater than mu 2, so the mean for group 1 is greater than the mean for group 2 on the dependent measure. Or if we wanted to extend this a little bit more, we could say mu 1 minus mu 2 is greater than 0. And so in that particular case, we're specifying a direction of the difference, not only that there is a difference. Another type of alternative hypothesis, a directional alternative hypothesis, would be where we state mu 1 is less than mu 2. Or we could say mu 1 minus mu 2 is less than 0. So you have to keep in mind which type of alternative hypothesis you're working from. If you are stating a non-directional hypothesis, then you're only concerned with whether or not the means that are observed represent a significant difference between means at the population level. If you are specifying a directional hypothesis, then it's not only an issue of whether there's a difference in means, but also whether that difference is observed in the hypothesized direction. So a non-directional hypothesis basically implies a two-tailed test. A directional hypothesis implies a one-tailed test. So looking at our test results down here, you can see that we have our t-test that's given to us right here. So these are, and we're going to concentrate mainly on this first row right here, the results here. So the mean difference between the two groups is negative 25. And so this is just basically calculated by taking essentially the mean for group 1 and subtracting the mean for group 2. And that's why we have a negative value right there that's shown as the mean difference. It's just basically the 361.8 minus the 387. So that's the raw score difference between states with and without the death penalty using excuse me, that should be X bar right there. Basically taking the mean for the non-death penalty states and subtracting the mean from the death penalty states from it. So that's basically what this difference is. Now, what is this difference statistically significant? Meaning that, if I say that this difference is statistically significant, then I would go back and I would infer that there's a significant difference between the means and the population. So again, in considering that question, I have to consider what the nature of my hypothesis was. So let's just say, for argument's sake, my research hypothesis was that there would be a significant difference in the population means between the two groups. So in other words, we have a lack of equality in those population means. So what I can do is I can carry out my t-test, and we already see that there appears to be a difference, but we don't know if that difference is great enough that we should attribute it to a real difference and not to sampling error. So the simplest way in using our output is to consult our p-value that is given right here. So and the basic rule of thumb is to, what we can do is we can compare our p-value versus an alpha level. So alpha is basically our threshold for committing a type 1 error, our tolerance for committing a type 1 error if the null hypothesis is indeed true. So conventionally, alpha is set at 0.05. There are times where researchers will increase or decrease alpha, but the conventional alpha level tends to be 0.05. And so in terms of rejecting the null hypothesis, what we're going to do is we're going to compare the p-value that is given right here against the alpha level. And if the p-value is less than or equal to alpha, then we reject the null hypothesis and infer that indeed there is a significant population mean difference between the two groups. If p is greater than alpha, then we would maintain the null hypothesis and infer no difference between the groups at the population level. So in other words, we have essentially one population group represented that's reflecting the composite of the information from the two groups. So you can see right here that the p-value as it's given, it says sig right here, two-tailed, and so if we're testing a non-directional hypothesis, we can see right here that the p-value is 0.564, which is greater than the alpha level that we laid out. So the alpha level is what you kind of approach the problem with, and then we're determining if the p-value is less than or equal or greater than the alpha level. So given that the p-value right here is greater than alpha, we would not infer that there is a significant population mean difference when it comes to differences between states with and without the death penalty in terms of the violent crime rate. Now, if I was testing a directional hypothesis, then let's say, for instance, I was laying out my hypothesis and it happened to be the case where I was assuming for whatever reason that the mean of the violent crime rate in the no death penalty states would be greater than that in the death penalty states. So in that particular case, that would be my hypothesis. And in this case, you can see the difference between the two groups is contrary to that hypothesis. So if that's the case, then I would not be able to reject a null even if this p-value happened to be less than the 0.05 level. It's very, you have to keep in mind that the direction of difference has to be that you're observing has to fall in the direction that is hypothesized in order for you to be able to reject the null. So, if my hypothesis had been that mu1 is less than mu2, the direction of difference is obviously clearly in line with the hypothesis, but the p-value is greater than 0.05, so I would not be able to reject the null. So that is a lot of the hypothesis testing process. Let's try another example. Let's go to compare means, and let's say that instead of looking at violent crime rate, let's look at total pupil spending. So I'm going to use an education variable just to see if there's a difference between the two groups. So in other words, we would be addressing the question of whether there are differences in the average total pupil per spending or pupil spending between the death penalty and non-death penalty states. So I'll leave the grouping variable where it's at, and I'm going to click on OK right here. And so now looking at our output, we can see again, we have our sample ends. So this is the non-death penalty end and the death penalty state ends. And in terms of the means, we see that the mean for total per pupil spending was actually greater among the non-death penalty states as opposed to the death penalty states. When we look at our t-test right down here, this is the t-test, and then we have the mean difference. So you can see that if I take the mean for the non-death penalty states and subtract from it the mean for the death penalty states, you can see that the average per pupil spending is about $4,000 greater in the non-death penalty states as opposed to the death penalty states. Now, is that difference significant? Well, that's again where I have to consider my hypotheses. So the null hypothesis, again, is essentially no difference between the two groups. So I'm just going to say mu1 minus mu2 is equal to 0. Or again, we could just say mu1 is equal to mu2. So in terms of the alternative hypothesis, if I was testing a non-directional hypothesis, then it would just be that mu1 minus mu2 is not equal to 0. Or we could say mu1 is not equal to mu2. And so if that's the case, well, we do see that there is a difference in the average per pupil spending between the two groups. Now, is it statistically significant? That's where we are going to consult our p-value associated with our test results right here. So you can see that we have a p-value that's equal to 0.000, and this is actually a rounding thing more than anything else. So basically, if p is presented as 0.000, then typically when people write it up, they're going to report a p-value as less than 0.001. So it's just basically rounded off. It's never technically 0. So in this particular case, we would infer that there is a significant difference between states that support the death penalty or that have the death penalty and those that don't in terms of the average levels of per pupil spending. Now, if I was testing out a directional hypothesis instead, then I would be carrying out a one-tailed test. And so let's just say that, if I had my my research hypothesis had been laid out in this way, let's say it was mu1 minus mu2. Let's say I was hypothesizing that states without the death penalty would spend more per pupil. Then I would lay it out as mu1 minus mu2 is greater than 0. Or I could state just simply mu1 is greater than mu2. In this particular case, you would see that our mean difference was in the hypothesized direction and we would have evidence of statistically significant finding there. If, on the other hand, let's say that my research hypothesis or alternative hypothesis had been the opposite direction. Let's say that I was hypothesizing that states without the death penalty would actually spend less on pupils than states with. And I would say mu1 is less than mu2, or again, I could state it as mu1 minus mu2 is less than 0. If that were the case, we would see a mean difference that is actually contrary to the stated research or alternative hypothesis. So even though the p-value would signal perhaps a significant difference between the two groups, because my research hypothesis, because the outcome in terms of the mean difference is contrary to my research hypothesis, I would have to maintain the null hypothesis and conclude no difference between the two types of states in terms of whether or not they have the death penalty. So you have to keep in mind that it's not only the p-value that is of relevance in judging statistical significance. When you're dealing with a directional hypothesis, the direction of the mean difference has to be consistent with your original hypothesis. So, and basically this whole testing process is relying on the t-distribution. So essentially you could think about it this way, that we have a sampling distribution of t, and at the center of this distribution lies a null hypothesis. So the null hypothesis is no difference between the two groups. So mu1 is equal to mu2, or again, we could say mu1 minus mu2 is equal to 0. And so what we're doing is we're looking at our data to determine if this mean difference departs far enough from the null hypothesis to infer that there is a difference between population groups. So, and in fact, let me just kind of re-specify this just a whisper. I'm just going to, because it's a little bit more intuitive this way, I'm just going to say mu1 minus mu2 is equal to 0. That's the null hypothesis. So what we're doing when we're testing our null hypothesis is when we set alpha, we are essentially setting a threshold within the sampling distribution of differences in means in order to sort of identify a point where we move from maintaining the null to rejecting the null. So if I set alpha at 0.05, and let's say I'm carrying out a two-tailed test, testing a non-directional hypothesis, then essentially I'm drawing essentially a line in the sand, so to speak, where within this region, if I observe my sample mean difference falling within this region, then I'm going to maintain the null hypothesis and infer that the population mean differences are equal to 0. Whereas if I observe a sample estimate that puts me out in this area or this area, then these are called the region of rejection, in which case we would reject the null and infer that there is a significant population mean difference between the two groups. So essentially all we're doing is we're converting the mean difference that we observe in our sample data into a t-value and then using the t-distribution in order to test this out. So at the center of the t-distribution is actually a t equal to 0. And again, we're looking to see if there's a significant departure from the null in order to determine whether or not we can reject it. So that's the basic idea behind that point. If we're testing a directional hypothesis, then we're still using the t-distribution, terribly drawn of course, but we would still have the t-distribution. At the center of the distribution, we still have the null hypothesis. And if we specify for our research hypothesis that mu1 is greater than mu2, which again would stated differently, would be mu1 minus mu2 would be greater than 0, then we're testing in the upper tail of the t-distribution. If the alternative hypothesis happened to be mu1, we'll just say mu1 minus mu2 is less than 0, then we would be testing not in the upper tail, but rather in the lower tail of that distribution. So that's how it essentially works. So another couple of things to kind of point out. You also have over here, you have Levene's test for equality of variances, and What this test is really aimed at doing is testing an assumption related to the independent samples t-test. One of the assumptions related to this test is that you have equal variances on your dependent variable between the two groups. So, and the variance for the dependent measure in the two groups is essentially nothing more than the square of the standard deviations for those two groups. So what we're doing is we're testing whether there's a significant difference between the two groups and their variances. And if there is a significant difference, then that means that we will have violated an assumption that is a requirement for carrying out the t-test, or the standard independent samples t-test. And what that, the reason why this matters is because if you violate an assumption related to the standard parametric test, then that can lead to decisional errors, meaning that it can yield an increased likelihood of committing a type 1 or type 2 error. So we don't want that to be the case. So this test right here, Levine's test, is a test to determine whether or not, or it can be used in determining whether or not that assumption of equal variances holds between the two groups. And so in that case, when we look at the significance level that's printed out right here, we can still adopt an alpha level at 0.05. And the thing about it is that in this particular case, we're sort of shooting for a p-value because the significance value right here is a p-value. We're actually shooting for a p-value that is greater than 0.05. So unlike the standard independent samples t-test, where we're oftentimes kind of shooting for statistical significance, when it comes to Levine's test, we're actually find ourselves shooting for non-significance. And so in this particular case, the p-value is 0.103 and it's greater than 0.05. So that would lead us to infer that there's no difference between the two groups in terms of their variances. And then that leads us to feel more confident that we have an accurate test results when it comes to our t-test. If this value, the significance level, had been, say, less than or equal to 0.05, then that would lead us to have some concerns about whether or not we could trust our original t-test. And instead, what we can do is, rather than relying on the standard parametric t-test, we can actually go down to this next row right here where it says equal variance is not assumed. And this is also a t-test, but it's essentially, it does not make the same requirement as the standard parametric t-test right here. And essentially what the second row, the test results, are essentially an effort to correct our test results in order to remove or decrease the likelihood of committing type 1 or type 2 error. So in this particular case, there was no need to utilize the equal variances not assumed version of the test. This is basically Welch's test. And we can still stick with the equal variances assumed, basically our standard parametric t-test. Another thing to kind of note in looking at our output, we have 95% confidence intervals. So essentially these are intervals that are formed around the mean difference that you observe right here. So it's essentially, at the mean, it's $4,007. That is the difference between the groups, and so that's just, again, taking the difference between the two groups in terms of total pupil spending. So that's the difference, and essentially we can lay out a 95% confidence interval, which is what you have right here, and this gives a lower bound and an upper bound. So it provides basically an interval estimate of the difference in means between the two groups. So that's essentially what's going on with that. So that is sort of a short, or maybe not so short, discussion of the independent samples t-test using SPSS.